Hello, my name is Hayden Schulz. I'm a fourth year mechanical engineering in Dr. Hassan Rashidi's design and manufacturing class, and today I will be presenting my Project 3. Here's a brief overview of my presentation. I'll first be talking about design for X, then moving into diffusion of innovation, chip mechanics and strategies, machining with an end mill, and electrical discharge machining. Design for X covers a multitude of factors, including manufacturing, assembly, disassembly, human factors, sustainability, maintenance, and ease of use. This is very important because it both answers the question of how and why almost every single component and assembly is made. Design for manufacture aims to reduce costs, decrease assembly time, simplify inventory management, use materials wisely, and consider feasible tolerances. A real-world example of this would be Tesla's Model Y rear underbody. Tesla implemented a single-piece casting for the Model Y's rear underbody using a giant casting machine known as a gigapress. By doing so, they were able to reduce parts and completely streamline their assembly. Design for assembly aims to reduce the number of parts, decrease overall complexity, create self-locating features, standardize fasteners, and reduce the number of tools needed. IKEA does an incredible job of this. Their flat pack furniture is easy to assemble and doesn't require any specialized employees. Design for human factors focuses on the following features: a user-centered design, ergonomics, intuitive functionality, safety, and accessibility. An example of this is the Herman Miller office chair, where they focus on supporting the body's natural posture and movements to reduce physical strain during long hours of sitting. Diffusion of innovation is important because it characterizes a product's life cycle in terms of consumer interest. There are 5 main sections to this. The innovators are the first to adopt an innovation, and they are the risk takers. Early adopters act as opinion leaders and can influence others to try new products. The early majority adopts innovations after seeing others' positive experiences. The late majority is very skeptical and more resistant to change, and they wait until the most of the community has adopted until they feel like it is necessary or unavoidable. The laggards are the last to adopt, and they tend to resist change until they feel like it's absolutely required. Most prominent example of this is Apple. The iPhone was introduced in 2007, and innovators and early adopters quickly bought into the product due to its novel touchscreen interface and mobile internet capabilities. They promoted these benefits to others, and the early majority followed once they saw the positive reviews and saw how the iPhone could enhance productivity and entertainment. The late majority soon followed after as they saw smartphones becoming essential. Finally, the laggards eventually adopted when finding a non-smartphone option became challenging. It is important to note how the diffusion of innovation is a continuous cycle that starts over after a new iPhone is released. This process really lays the framework for how products are viewed and interacted with in our society. Let's take a look at chip formation and its multitude of variables. The independent variables include type of cutting tool and its properties, shape of the tool, surface finish and sharpness, workpiece material, and cutting speed, feed, and depth of cut. The dependent variables include force required, energy dissipated, temperature rise in workpiece, and type of chip produced. Let's take a deeper dive into continuous chips. Its advantages include producing a smoother surface finish. It results in a more efficient material removal due to its steady cutting process. It has lower tool wear since there is a minimal interruption in the cut. Its disadvantages, however, are long chips can entangle around the workpiece or spindle, leading to safety hazards, as shown in this picture on the right, and it requires chip breakers or specialized tooling to control the chip length. Some of these solutions are chip breakers, which most modern cutting tools, such as CNC machines, are equipped with. and coolant application, which can help control the temperature and prevent excessive chip length. Let's look at discontinuous chips. Some of its advantages are shorter chips reduce the risk of entanglement around the workpiece tool and improve safety. It has lower cutting forces required than a continuous chip. It reduces heat buildup due to breaks in the cutting process. Some of the disadvantages are it can result in a poor surface finish, and it has higher tool wear, and it also requires more management. Industry solutions include tool geometry optimization, where tool materials and cutting angles can be optimized to manage chip segmentation without overstressing the tool. Another solution is controlled cutting parameters, where adjusting the feed, speed, and depth of cut can help stabilize your chip formation. Let's take a look at end milling. End milling is one of the most versatile machining processes. It allows for the formation of complex shapes with detailed contours, and it is applicable to a wide variety of materials. It has high efficiency, and it is capable of hitting very tight tolerances. There are many machines that use end mills, ranging from a 3-axis manual mill all the way to a Mazak, which is a 5-axis CNC. End mills are capable of performing a variety of operations, including slotting, profiling, contouring, plunging, face milling, and pocketing. End milling provides a high degree of precision, often within microns. It is suitable for cutting a wide variety of materials, including metals, plastics, and composites. End mills are available in various sizes, shapes, and materials, including carbide, high-speed steel, and coated variants. And roughing end mills can remove material quickly, making it efficient for roughing large parts. End mills are generally limited in the depth of cut due to deflection and increased cutting forces. They experience wear, especially at high speeds and with harder materials. They are prone to vibration and chatter, which reduce surface finish, and custom end mills can often be very expensive. Here is some of the work I did over the summer at Georgia Tech's manufacturing facility. I created a Basler camera holder, I completed the Montgomery Machining Mall test part, and I built a table for a wire arc additive manufacturing system. All of these were completed on the manual mill. Now for my favorite manufacturing method, electrical discharge machining, or EDM. EDM works by creating a series of controlled electrical sparks between an electrode and the conductive workpiece submerged in a dielectric fluid. The electric discharge generates intense heat, causing small amounts of material to vaporize or melt from the workpiece at each spark site. Some of the common types of EDM are sinker EDM, wire EDM, pictured on the left, and hole drilling EDM. EDM is capable of machining very hard materials such as hardened steel, tungsten carbide, titanium, and superalloys. It can achieve extremely tight tolerances within microns, making it ideal for tooling and die making. Since EDM involves no direct contact between the tool and the workpiece, there is minimal mechanical stress and no risk of burrs. The limitations, however, are that it is slower than traditional machining methods, as it removes material in small amounts with each spark, making it less efficient for high volume production. The electrode in EDM also gradually wears down as it is consumed during the process, especially in sinker EDM. This significantly increases your costs. EDM also requires a conductive workpiece, limiting it to metals and certain conductive composites. Non-conductive materials such as plastics, ceramics, and composites cannot be machined by EDM. I was able to use a wire EDM over the summer to make a camera cover that protected a Basler from spatter inside a CNC machine. Another fun project I worked on was a GT logo bottle opener. It is very cool to see the texture of the aluminum where it was cut by the sparks. Thanks for watching my video. I hope you enjoyed learning about some of the models, strategies, and processes that are used in the manufacturing world today.